In this module, we will learn a couple of things. So, we will start with experimental determination of a transfer function. So, what we had learnt earlier in terms of modeling was you have a system, you first build a physical model of the system. Physical models would mean that you realize it with some basic components. If it's from electrical domain, you will have resistors, capacitors, inductors. From mechanical domain, you will have equivalent elements in terms of mass, spring, dampers. You could also model electromagnetic coupling and so on. And once you have the physical model, what you would do is write down the physical laws like the KCL, KVL, the Newton's laws, and arrive at a mathematical model. So, another way to do is what if I do not have any information on the system? I may not be able to realize it with physical components, and therefore I may not be able to directly write down the transfer function in terms of, or first by writing down the KCL and KVL kind of things. So, can I do something else? Can I start with determining the transfer function with the help of experiments? Okay, so we need to be careful while we do that. So, and that leads first to define the concept of minimum and non-minimum phase systems. So, I'll briefly run you through these things before I tell you why we need these things. So, systems which have neither poles nor zeros in the right half S plane are minimum phase systems. So far we characterized poles being on the right hand side and identified them with essentially unstable systems. We never talked about zeros either on the left or on the right. All we knew while we were drawing the root locus was that the poles go to the zeros and so on. So, now what are these non-minimum phase systems? So, these are systems which have some number of zeros, a finite number of zeros in the right half S plane. Okay, so how do I identify when is a system a minimum phase or a non-minimum phase? So, there could be several systems with the same magnitude characteristic. For example, if I, and also revisit this example. So, if I have a transfer function which is like s plus 1, s plus 2, and I compare it with a transfer function s minus 1 and s plus 2. If I plot down the magnitude characteristics, both of these systems will have the same magnitude characteristic. Okay. Now, how do I identify which is, so by just by looking at the magnitude plot, I may not know if it is a minimum phase or a non-minimum phase. So, what happens in the in case of non-minimum phase systems is that the range in the phase angle of the minimum phase transfer function is minimum among all such combinations, right, all such systems which have the same magnitude characteristic. So, you have same magnitude characteristic here and here. How do I identify which one is the minimum phase? You just look at the range in the phase angle of this guy and the range in the phase angle of this guy, and you take that one which has the minimum range, right. The range in the phase angle of the minimum phase transfer function is the minimum along all such systems, right. So, I'll show you some plots also shortly. So, while the range of any other thing would be, so if this one is the minimum, any other thing would be the non-minimum characteristic. And now, for a minimum phase system, the transfer function can be uniquely determined by the magnitude curve alone. So, once I know this, I can do something nice, right. So, if I just give you a magnitude characteristic, this is my frequency, this is my magnitude g of j omega, it looks something like this. Then I know that this is essentially what I do is a Bode plot, and with the corner frequencies, the gains at say omega equal to 1, I can actually write down the transfer function here. Okay. So, for that I need to first make sure that I know that my phase would be of minimum phase. So, for a minimum phase system, the transfer function can be uniquely determined from the magnitude curve alone. So I will assume that whenever I am doing this experimental determination, that my system would be minimum phase. Okay, so more on this will keep coming. So what are the other ways how of distinguishing between minimum and non-minimum phase? So for a minimum phase system, the magnitude and phase characteristics are uniquely related. So just take any minimum phase like this. So given the magnitude plot, there will be a direct one-to-one relation with the phase plot. So if the magnitude curve is specified over entire frequency range, then I could also find the phase angle curve. Okay, so non-minimum phase systems, okay, what do they, why are they not really good for us? And I'll spend an entire lecture on analyzing these 3 bullet points which are coming up. So non-minimum phase systems are slow in response because of the faulty behavior at the start of response. So if we remember while we were in one of the earlier modules, I think in number 7, we were looking at the role of zeros in speeding up the response. There is also one plot where we talked about a zero being on the right hand side where we experienced an undershoot. So I'll spend time on that in the next lecture. For the moment, we will concentrate on determining experimentally the transfer function of a system. So a common example, we'll again come to these examples, is that of a transport like systems. So when can non-minimum phase situations arise practically? Well, if the system includes non-minimum phase elements, right? Again, we'll do this, revise these examples or revisit these examples in detail, or when internally there is a minor loop that is unstable. Okay, now what are further techniques? Just look at the transfer function or the phase characteristic and the magnitude characteristics. Is there any way we can identify between minimum and non-minimum phase systems? So for a minimum phase system, as the frequency tends to infinity, right, the phase angle becomes minus 90 q minus p. Well, this is just the difference in the number of the poles and the zeros, right, where p and q are the degrees of the numerator and the denominator, or essentially number of poles minus number of zeros. For a non-minimum phase system, this will not be true, that the phase angle as omega tends to infinity will be different from this number. However, in either case, right, it could be a minimum phase or a non-minimum phase, the slope would be equal to this guy. So the slope at omega equal to infinity or as omega tends to infinity would be equal to minus 20 or some multiple of minus 20, would be equal to minus 20 q minus p. So the multiple will come over here. And if the slope of the log magnitude curve is equal to minus 20 decibel per decade and the phase angle is again minus 90 q minus p, then the system is minimum phase, else it is non-minimum phase. So what uniquely determines if it is minimum phase or non-minimum phase is this number or the phase angle minus 90 q minus p. Okay, so let's start with an example, right? So I consider a transfer function 1 plus st1, 1 plus st2. Both of them are greater than 0, and let's assume for simplicity that T2 is greater than T1, or in other words, the 0 lies to the left of the pole in the left of plane. So it's a stable system, and also minimum phase as per the definition which we just had. So well, both poles and the zeros lie in the left of plane, so the transfer function is a minimum phase transfer function. Now look at the magnitude and let's compare with what we had said over here in these 4 bullet points. So the magnitude and the phase can be determined like this way. So g1 of g omega would be the magnitude of this guy and the magnitude, so something like this. Similarly with the angle, right, the angle contribution of this minus the angle contribution of this one. So as omega tends to infinity in this case, we see that the magnitude goes to the 0 dB line, or in absolute terms it will just be 1, and the angle goes to 0. So what should be from here? So the magnitude for a minimum phase system as omega tends to infinity should be minus 20 q minus p. What is q in this example? What is p? Both are equal to 1. So, what is minus 20 q minus p? That should just be 0. Q minus p is 0. Therefore, we see that as omega goes to infinity, the magnitude goes to 0. Okay, what happens to the angle? Well, as the angle as omega increases and goes to infinity, we can see that the angle goes to 0. Now, is this consistent with the definition here? Well, the angle should become minus 90 q minus p. Q minus p is 0, therefore, the angle contribution should be 0, right. So, based on these observations here or these remarks, we can notice that the magnitude and the phase satisfies the properties of a minimum phase system, both the magnitude criterion and the phase criterion. Both are 0 because q and p both are equal to 1. Now, as a contrast, just take another example where I have a 0 in the right half plane. The system is still stable, by the way. So, G2S is 1 minus ST1, 1 plus ST2, T1, T2 again greater than 0 with T2 being greater than T1. The 0 lies in the right half plane. So, the transfer function as per our definition is a non-minimum phase transfer function. Okay, so let us do all the comparison of the magnitude and the phase again. So, G2 of j omega, so this magnitude is like this and it is exactly the same as in the previous case. So, the magnitude just remains the same, and therefore, even as omega goes to infinity, the magnitude will go to 0 dB, nothing will change here, right. So, this does not give me any information if my system is a minimum phase or a non-minimum phase. Okay, let us go to the angle. Well, if I do this one and my angle now is negative of tan inverse omega T2 plus T1 and so on. Slightly little different, right. So, you have a T2 plus T1 here instead of a T2 minus T1. Okay. So, now if I compute the angle as omega goes to infinity, I can easily check that the angle goes to minus 180 and this is not equal. So, this angle is not equal to minus 90 q minus p. Q minus p in our case is 0, therefore, this angle if it is a minimum phase system should also be 0. And since this does not hold, we say that the system is a non-minimum phase, right, from these two conditions. So, sorry, this condition, this is satisfied trivially, but this condition is not satisfied. Okay. So, to conclude our observations, both G1s and G2s have the same magnitude criterion, but they have different phase angle as omega goes to infinity. G2 has minus 180, G1 has 0 degree. G1 satisfies this criterion minus 90 into q minus p, whereas G2 does not, and therefore, G2 is the non-minimum phase, and because of this definition of the 0 being on the right hand side, it satisfies these 4 conditions. Okay, so if I were to just plot this, right, for some values of T1 and T2, you see that this is G1 and it starts from 0, goes back to 0, G2 will start here and then go to minus 180. Again, so given these two, how do I identify which one is minimum phase? Well, I go here, because if I say I just do not know what is the number of, or what are the number of poles and zeros. So, I take the phase plots and I say the range in phase angle of the minimum phase transfer function is the minimum among all such systems. Okay, so the range in the phase angles, here it goes 0, say minus 45, and here it keeps on going down. So, this is the minimum phase system, and this is the non-minimum phase system because of the range also of the phase angles. So, I need not always uniquely, if I do not know what is the number of q's and p's, I can make use of the other definition. Okay, so now this brings us to the question which we started with. Can we experimentally determine the transfer function? And by experimentally determining, I say, well, can I subject my system to different frequencies and look at the magnitude plot? Okay. So, as we saw earlier, the first step in analysis and design was to derive a mathematical model. The mathematical model which we dealt or which we used so far very extensively was the transfer function. Sometimes it may not be possible analytically, or even I may not even have any information of what are the physical components sitting in the system. Therefore, I employ a technique where I can just plot the frequency response of the system and see if I could get to the transfer function. So, I measure the amplitude over a large range of frequencies, and because of this I can easily plot the Bode. So, Bode essentially was that, right? I am looking at how my magnitude changes, which changes in frequency, and the transfer function can be determined by the asymptotic approximations, and I will show you a couple of examples how we do this. And of course, I can just keep on adjusting the corner frequencies until I get as close to the real model as possible. And we also know how to uniquely determine what were the errors associated with the corner frequencies for each of the cases. I have a 0, a pole, complex conjugate poles and zeros and so on. Okay, so first we will just recollect Bode plots. So, this is just recollecting Bode plots in a reverse way, right. So, first I just draw asymptotes of all the Bode plots, and well, all these asymptotes must be of multiples of plus minus 20 dB per decade, depending on if it is a pole, if it is a 0, if there are multiple poles, multiple zeros and so on. So, if the slope changes by minus 20 dB per decade, then I know that there exists a factor resembling a pole like this. Just remember what we did, recall what we did while we were constructing the Bode plots. So, I am just doing the reverse of that. And similarly, if there is a slope of plus 20 decibels per decade, then I am actually looking at a 0. Okay. Now, this is again, I assume that everything is minimum phase, and therefore, I could do this. And similarly, if the magnitude changes by minus 40 decibels per decade, then there exists a factor something like this. These are complex conjugate poles, and similarly for plus 40 it would be complex conjugate zeros. And then the undamped natural frequency here is the corner frequency, and the damping ratio can be found out by measuring the amount of resonant peak near omega 2. So, we had plotted the Bode for different values of zeta at the corner frequencies. So, based on those observations which I had earlier, I could get an estimate of what is the damping ratio. Okay. The gain can be determined from the low frequency region, right, and we also saw how the low frequency region also helps me low frequency region helps me estimate the error constants Kp, Kv, Ka, and these are directly related to the low frequency gain, right. So, the low frequency behavior, I can find out what is the gain of the system, and well, these are all we know. So, we know this from earlier, right, at low frequencies. So, these derivations we did when we were looking at computing the error constants from the Bode plot. So, at low frequencies I am just interested in these kind of things. There could, where beta is like the type of the system. If it's just a type 0 system, g of j omega equal to k for very low frequencies, or in the log scale 20 log g of j omega would just be 20 log k, right. And then in this case, the low frequency is behavior is just a horizontal line at minus 20 k dB per decade something. So, it will just be something. So, it will just be a straight line of minus 20 log k, and just be a constant line across all frequencies if I just keep on drawing this. So, this is a low frequency behavior when I have a type 0 system. Similarly, for a type 1 system, so g of j omega can be approximated for very low frequencies as k over g of j omega, and I see that the behavior is something like this, okay, which indicates that the low frequency has a slope of minus 20 dB per decade, and where it intersects the 0 dB line, this was my constant, or this constant was also equal to the velocity error constant. Similarly, for type 2 systems, I will have a slope of minus 40 decibels per decade, and the intersection with the 0 dB line will tell me the gain, right? With this, we derived these formulas, right, when we were looking again at how to determine Kv and Ka directly from the Bode plots. Okay, so just as an example, so how do we do this? So just say I just do a frequency testing of a signal. I subject frequency testing of a system. I subject my system to several frequencies, and I see a plot like this. Okay, so and I say, well, now if I say that I do not know anything of the system, I just give you this plot, just the magnitude plot, forget even the phase for the moment. If I just have the magnitude plot, can I find out what is the transfer function? Okay, the way we do this, the way we identify now the transfer function is to first construct an asymptotic plot of the magnitude plot of the Bode. As said earlier, I am not too worried about what happens in the phase plot because I am essentially dealing with a minimum phase system, in which case I can purely determine my transfer function based on the asymptotic plot. Okay, so what happens first in the low frequency region? Well, if I know that if it were just a straight line, then the system would be of type 0. Now there is some initial slope, so the system is no longer of type 0. It could be type 1, type 2, type 3, and so on. So let us find out what is the slope of this one. So I start here at a frequency of 0.1. I reach a decade here at 10 power 0. This is 1. So let's measure the magnitude. So here I am roughly about 38 dB, and I go down, and then where is the point where I am at 10 power 0. So I am somewhere here. I go here and say I am roughly about 18. So in a decade from 0.1 to 1, my slope has decreased by 20 decibels. So this is 20 decibels per decade, right, which means I have a system which is now of type 1. Okay. Now second thing what we need to identify are the corner frequencies. So I start at as a slope at 20 dB per decade here, and I see that my slope changes from minus 20 to 0 dB here, right. So at this corner frequency, so we'll identify what this is. So I start with, sorry, this is minus 20, this is 0 decibel per decade, and I keep going, and I see that again at this corner frequency I am at plus 20 decibel per decade, and I go here again at somewhere around this frequency, again it becomes 0 dB per decade. Then at this frequency I am at minus 20, and here I am at minus 40. Okay, so so let's see. So here this is a type 1 system, so I'll definitely have 1 over S kind of thing, or a pole at the origin. Okay, so I also need to identify what is the gain case, so we'll come back to that. So okay, so start from here. So here what is this corner frequency? If I go here, this occurs roughly at a corner frequency of 1.7. okay. Now next I go further. So this is now I start at minus 20, I go I increase the slope by, or I encounter a quantity which increases the slope by plus 20, so there is a 0 here. Similarly at this frequency, which is about 4 radians per second, I can just measure it through this lines here, 4 radians per second, I encounter another 0 because the slope increases from 0 to 20. At this frequency, which is roughly about 8, the slope decreases from 20 to 0, so I have a pole. Again at this frequency I go, which is roughly about 17, again there is a pole, and so on until, so the slope decreases from 0 to minus 20, minus 20 to minus 40 here. So also here there is a pole at a frequency of about 42 radians per second. Okay. Now the next thing to find out is what is the gain K. So the way we find out the gain is, it is the value at which the initial slope intersects the 0 dB line. So here, Okay, that's we also saw this when we learned how to compute the velocity error constant through the Bode plot. So this is 8. So my constant k, which sits in the numerator, where the initial low frequency region is of this form. So the k is simply found to be 8 by the intersection of the initial line with the 0 dB line. Okay, now things are straightforward, right? So I just can write down my transfer function of the form g of j omega is, now I have the gain, this is the low frequency behavior, I am just writing down the sinusoidal transfer function. Then what happens after this? I encounter a 0 at 1.7, so this would show up in this way, j omega by 17 plus 1. After that there is another 0 at a frequency of 4 radians per second. So this will be, this is 1.7, sorry, j omega by 4 plus 1, and then after 4 I am at a corner frequency of 8, right. So where the slope now decreases from plus 20 to 0, therefore I encounter a pole here, j omega over 8 plus 1. Similarly, I have another pole at 17 and another pole at j omega by 42 at 42, where the slope now becomes minus 40 decibels per decade. So what is the simple process that we follow here, right? So we start with first by experiments. These experiments lead to a frequency response which is the Bode plot. From this Bode plot I can construct the asymptotic plot, and finally from this asymptotic plot I can find out what is the transfer function of the system. Again, the key is the assumption of minimum phase. Okay. So let's do another example where I am directly given the asymptotic Bode plot. So things are much easier for me here. Okay, so how do I go about doing this? So first is, well, I have this low frequency behavior, which I can say that, well, my numerator, or which this is like 20 dB per decade, and therefore there is a something like a 0 at the origin. Okay, and then there is, so what is this corner frequency? So at omega equal to 3 I am at 0, and I pass one decade to be 20. So this, what is a decade? You multiply by 10, this is 30 radians per second. Okay. Now similarly, now I go here and there is another corner frequency here. So at this point I want to find what is this corner frequency. I am at 20, I go to 0 at 500, and this all happens in a decade. And again, what is a decade? So here I divide by 10. This is at 50 radians per second. Okay. So now I have something like a 0 at the origin, then one pole here and another pole. Now something strange is happening here. Okay. At omega equal to 3, my magnitude is 0. At omega equal to 1, well, I do not really know what this is. Okay. So now these are just straight lines at which go at 20 decibels per decade if I look at in the log scale. So what I would know, so if I just call this as omega 2, omega 1, so what I know is that log of omega 2, okay, I will just write it in a different way. Compare with the y axis, right. So what is on the y axis? So I have 0, let me call this some number y, so this magnitude here 0. So y2 minus y1 by x2 minus y1 is the slope, right. That is what we learn in coordinate geometry. So here on this axis I have log of 3 minus log of 1 is 20. Okay, so now from this I have y is minus 20 log of 3. This means y is minus 9.54 decibels. Okay. Now, I should find what is the value of gain k. So, I compute it in the following way. So, at omega equal to 1, so I have 20 log of k is minus 9.54, and this gives me a value of k as 0.33. Okay. So, now I just want to write down my transfer function. Okay. So, g of j omega, I know well it has a 0 starting from the origin, a gain at 0.33. What happens after this? So, from here till here I have a pole now, right. My slope decreases from 20 dB per decade to 0. It is like a minus 20 from here, right. So, there will be a pole. Now, what is the corner frequency corresponding to that pole? That will be 30 radians per second. Okay. So, I write this down here. So, just this as j omega. So, this will be 0.33 j omega over 30 plus 1, and here this is a corner frequency of 50. So, this would be j omega over 50 plus 1. So, this is the overall transfer function of my system, and we can recheck this by just plotting the Bode of this. So, we get to this asymptotic plot, right. So, what we have seen, right. So, we have seen two examples where we start with a pole at the origin, we start with a 0 at the origin, and so on, right. So, this is now a very general procedure. We could apply this to several other systems. It's just a matter of some manual exercise, picking the asymptotes carefully and accurately, and you just arrive at the appropriate transfer function. Okay. So, what we have learnt here is, well, we started with the aim of experimentally determining a transfer function, but the catch was that we had to distinguish between minimum and non-minimum phase, and we said that, well, for a minimum phase there is a unique relation between the magnitude plot and the transfer function and also the phase, right. So, we learnt about these things, and then we plotted or we given a minimum phase transfer function, we learned how to get the transfer function from a Bode plot. So, I know that the system is minimum phase. So, we will next class we will see a little more on this effect of zeros. The effect of zeros to the left half plane we did quite extensively in module 7, even in module 8 while we were designing what we called as the lead compensators. Here we will see some strange behaviors of zeros being on the right half plane, or non-minimum phase zeros. So, that will be coming up shortly. Thank you.